So what I'm talking about is joint work with Terry Napier. So what I'm going to do is just state the theorem. I'll introduce what the terms mean, and then I'll explain the motivation for the question and things like that. So M is going to be a compact scalar surface. Connected. And then M tilde over M, a covering, infinite covering with covering group gamma, and rho from gamma to GLNC is a faithful reductive representation. By that I just mean every invariant subspace is an invariant complement. Also need one more assumption which I'll explain. So I want the number of ends of gamma to be not equal to 2. Then, and M tilde is holomorphically convex. So by a theorem of half, you can say that E of gamma equals 2 if and only if gamma contains an infinite cyclic subgroup of finite integers. So this is the statement of the theorem. Oh, sorry. Then, so I should say under these assumptions, then M tilde is 1. So let me define holomorphic convexity of a complex manifold or a complex space. So I'll just assume connected if necessary. So if K contained in Y is, say, compact, then the holomorphic convex hull of K is just such that absolute value of f of y is less than or equal to for all f holomorphic. Okay. Yes.
I missed it, but you said tilde the universal covering?
No, no, just some covering. Yeah. Sorry. Galois covering, yes. So then you say a complex manifold is Y is holomorphically convex if for every K compact, K hat is compact. So in particular, you can see that a compact manifold is holomorphically convex. So so when it's non-compact, so it's a theorem of Remmert. Y is holomorphically convex if and only if Y admits a proper holomorphic mapping to a Stein space. So you can think of it as just a complex subvariety of Cn. It's not really true, but so why is one interested in this question? So it turns out Schafarevich asked the following question at the end of his book on basic algebraic geometry. So is perhaps the universal cover of a smooth complete algebraic variety holomorphically convex. Of course, this was just based on a few examples. You looked at Stein spaces and you crossed it with projective spaces and then asked the question. Now, what is interesting is it turns out if you're interested in questions about holomorphic existence of holomorphic functions on, say, universal covers, those kind of questions, then it's natural then to ask if some intermediate cover at least has some holomorphic functions. And it turns out in practice you end up showing either you have lots of them or nothing at all. I mean, there seems to be no in between. I mean, to give you an example, this was an open problem till the 1940s of Carathéodory. Maybe I'll write it here. As every open Riemann surface have non-constant holomorphic functions. So it turns out this was actually a question of Carathéodory, and it was answered by Benke and Stein in the mid-1940s. So what they did was they showed that it's basically a Stein manifold, so you have lots of holomorphic functions by proving a Runge type theorem. So those and so in the question there, so of course if you start with, say, gamma being an abelian group, even then you only end up with holomorphic 1 forms. But let's say if you were dealing with the fact that you have a map to the Albanese and then you go to the corresponding covering, then you get a proper map to Cn, so you get holomorphic convexity. So that's sort of abelian Hodge theory kind of H1 giving you some information. So as usual, we don't know how to handle this without some hypothesis. So the first attempt is to try it for surfaces and assume that at least you have a reductive representation to start the process going. So that's where this assumption plays a role. And let me say where the ends of gamma equals 2 play a role. So these examples go back to Kuzan. He has a paper, I think, which literally translates to on triply periodic functions of 2 complex variables. So what we do is we look at C minus the origin cross C minus the origin. And lambda and mu are, say, multiplicatively independent. And absolute value of lambda is not equal to 1, absolute value of mu not equal to 1. So then I can quotient. So I have a product of 2 elliptic curves. I also have an intermediate cover here. So I'll call that. Running out of y. So what you do is you quotient by the cyclic group, which acts on ZW by multiplication by lambda, multiplication by mu on W. So this is actually a covering with covering group Z, and it has no non-constant holomorphic functions. Because what is a holomorphic function? It's going to be a Laurent series in 2 variables, invariant under the scaling. And if you choose lambda and mu generic, then this ensures that it's constant. So therefore, I need some assumption like this. I have to rule this out. So this is there. So then the question becomes, okay. So the other obstruction to, let's say, holomorphic convexity would be the following. So let's say we have M compact scalar, or you have a covering. So one thing you can see from the definition of holomorphic convexity is if you have an unbounded sequence, then you can find a holomorphic function which is unbounded along that sequence. And so what could happen is you could have a A contained in M tilde connected analytic positive dimensional further such that all irreducible components of A are compact. So if you had such a non-compact A, then this would be an obstruction to having holomorphic convexity for surfaces. It turns out, at least for surfaces, this seems to be the only obstruction. In 3 dimensions, you can ask what could happen. You could have this problem that a Cousin type example could be embedded there. So you could have a situation where you could have a compact scalar threefold. You could have an abelian variety sitting in here. And when you go to the covering, the image of it just could be Z, so it opens up only partially. And if it's a generic situation, this would be stuck in there. So it's a question of dealing with that. So this is the reason why we restrict ourselves to surfaces. So in case of surfaces, in the mid-90s, Katsarkov and myself proved this result. For M smooth projective. So the main thing I want to talk about is we found a completely different proof of these results, including simplifying the old proof, and it works for compact scalar surfaces. So here I want to make some comments. Philippe will be talking more about some of these things. So after we proved it for surfaces, Philippe Aisidiu, I'll just stick, proved that, so M is a smooth projective, but now no longer a surface. And you have a covering. I won't say exactly, you need some little extra assumptions over what we had here to rule out those abelian varieties kind of stuff. So then this covering, if it has a certain family of reductive representations, then this covering is holomorphically convex. You're looking at intersection of bunch of representations into absolutely constructible set of reductive representations. Okay? And then you look at the quotient of the universal covered by the intersection of the kernel, and you want to say that that's holomorphically convex. Then subsequently, Aisidiu Katsarkov Pantav and myself, we showed that if instead of just working with reductive representations, even if you have linear representations, again with a little more hypothesis, then the corresponding covering is holomorphically convex. Then more recently, Campana, Clodon, and prove this for compact scalar under this extra hypothesis. And in fact, one of the steps is the proof of the reductive case for compact scalar manifolds. So then the natural question became, can we extend this original thing for the surfaces which took the compact scalar case? So I want to talk about that. So people who are used to Stein manifolds think that, so let me start with the following. This is a famous Levy problem solved by Grauert. What? Well, it need not be holomorphically convex. If you take a half surface, for example, the universal cover is C2 minus 0. So you have Hartogs telling you that everything X. Yeah. No, it's just that, yeah. Scalar seems to be no difference. In fact, the question of whether there is a projective, a fundamental group of a smooth projective variety different from one for one which is normal, even we don't have examples. I mean, because all the Hodge theoretic arguments always seem to go through for involves H1 and they're works for normal things. So, and all of these things would immediately go through for any compact Kähler, normal one which has a Kähler resolution, for example. So, because the harmonic map theory works, so it's just that. So the Levy problem. So the question is, how do you prove that something is Stein or something is holomorphically convex? And this is the hard problem. So the classic one was X is so a complex manifold. So this is the theorem of Grauert. If and only if Y admits a strictly pluri-subharmonic exhaustion function. So I'll explain the terms. So that just means it's a function from Y to reals such that the exhaustion is just a statement that if you look at X sub C, which is not Y sub C, sorry. So this is relatively compact in Y. And let's assume the function is C2. So if you look at square root of minus 1 dd bar phi, this is positive. It's a Kähler form.
Just to check, what do you the definition of Stein?
Okay, so one definition, originally the way it was defined was it's holomorphically convex. You have holomorphic functions to give you, global holomorphic functions which give you local coordinates and separate points. So that was Stein's original definition. So if you have such a situation, you can just use those holomorphic functions to construct an exhaustion function, which is strictly pluri-subharmonic. In fact, in that case, it's even real analytic. Now, unfortunately, the moment you weaken it to be just semi-positive, nothing works. There is no theorem. So what you hope for is the following. You look at the degeneracy, and you hope that that could give you some kind of foliation, and you try to construct a quotient space where everything becomes Stein. I mean, this is the kind of thing you try to play with. And in case of complex spaces, this was proved by Narasimhan. Yeah, that is right. Yeah, but that if you use the Stein definition is a theorem. Okay. Yeah, absolutely. Yeah. In fact, the science spaces we will need always end up getting embedded in Cn because they always have bounded embedding dimension. because they come from equivariant maps to a covering. So what happens if you restrict it to be semi-positive? These Cousin type examples. So there is, in general, if you look at C star to the n, and you look at zk sitting inside as a Zariski dense subgroup for k less than n, they will always have as many positive eigenvalues for the Levy form as this, as k. So you'll just have one thing missing. I mean, the difference will be n minus k. Those will be zeros. And these things will never have any holomorphic functions. So let's kibosh on that. So the tools we want to use to prove this result is the following. So the goal, as I said, is going to be to look at this Levy form and then look at its degeneracy locus and then try to sort of show that the thing exists. So what are the difficulties? So let's start with our representation to GL and C. So I look at the representation variety. Yeah, so that's the Berry moduli space, gamma. So up to conjugation. Now, if our original if this component of the of this, which contains this original representation, if it's just a point, that itself will show most of the difficulties. So I'll illustrate it there. Analytical difficulties. Anyway. Is rigid, then we know that the image lies inside GLN of Q bar. So then what happens is you immediately get, so by taking a suitable completions with respect to Archimedean and non-Archimedean valuations, you can end up constructing a map from this to a X is going to be a product of Euclidean spaces, symmetric spaces, and buildings. So then the usual game is you try to, so X is non-positively curved. That's what you want to think of. So the Kähler package, so usually when you deal with one forms is you want to say it's harmonic and then you want to say it's pluriharmonic, which is just saying that the real parts are all holomorphic. I mean, sorry. Yeah. So by the work of Gromov and Shane, I mean, sort of the Eel Sampson. You end up with an equivariant pluriharmonic map to this building corresponding to the representation gamma, where gamma acts here through these representations. Sorry. Okay, so you look at the corresponding this mod the maximal compact, right? So you complete with respect to the various evaluations. So you'll get finitely many ones which correspond to either symmetric spaces if you have Archimedean valuations, and then we'll have buildings, affine buildings. So I take the product of those, take the diagonal embedding, and look at the action. How do I get a map like this? Because this space is contractible. Through the representation, I can construct a bundle, which is with contractible fibers, so it has always a section. And so then, so Gromov, I mean, as usual with all these things, we try to make it into something nice. So So this gives you that F is pluriharmonic, which is modulo implies the statement that if you have any holomorphic map from the disk to M tilde and you compose it, it's still harmonic. Okay. Harmonic you should think of as locally energy minimizing. So you can talk about the differential of this path. You can take the norm squared. It will descend to a function on M, which you can then integrate. Okay. So the main feature about pluriharmonic or harmonic maps here is if you take the distance squared from a point in X, this is actually a convex function. So when you compose a convex function with a pluriharmonic function, you end up with a plurisubharmonic exhaustion function. Yes? Yeah, that's the Keller package, yeah. So then if you look at distance squared, say of f of x, comma, I don't know, not some point here, then this gives you, yeah. So I have to use the fact that I'm making the representation discrete here because it's rigid. I've made it discrete so that this map is proper. This map is proper. Preimage of compact sets are compact. So therefore, distance squared composed with this is an exhaustion function, plurisubharmonic exhaustion function. So this, which I'll call phi of x, is a problem for us is, of course, such a function is only semi-analytic. I mean, away from a certain locus. But the problem you have is if you take a building, I mean, if it's just a symmetric space, then it's just real analytic. If you have a building, if you have an apartment, and if you restrict the distance squared to the apartment, all you can prove is it's semi-algebraic. Because you have branching, so that forces things to be locally maxes of various such functions. So for us, this doesn't have much regularity, but however, being actually semi-analytic is very helpful for us. So first point is, if phi from say y to r is plurisubharmonic exhaustion function, so here dimension of y is 2, and phi is generically strictly plurisubharmonic. By that I mean it's strictly plurisubharmonic away from a subvariety. So then in case of surfaces, you can then prove it's holomorphically convex. So the idea here is by a theorem of Narasimhan, it's enough to show that sublevel sets are holomorphically convex. So you have a strictly plurisubharmonic function, and what you can ensure is you can take level sets which avoid the compact components of this degeneracy locus. So if you look at where it hits this boundary, it will be a non-compact Riemann surface. So you can find Stein neighborhoods for it, and then you can patch these functions together to construct a function which is strictly plurisubharmonic in a neighborhood of the boundary, and then prove holomorphic convexity. I'm sorry? Sure, yeah. So what will happen is, so you have your degeneracy locus. So whatever compact pieces are lie inside here. So near the boundary, it's going to be a non-compact Riemann surface. So you can find a Stein neighborhood of this. Okay. Oh no. So I'm looking at phi less than c, right? Let's pretend that the things are smooth for the moment. So you look at a regular level set. So that's phi equals c. And then see where these degeneracy locus sort of, going off to infinity here inside or whatever you want to think of. So they have Stein neighborhoods. So therefore, you can find strictly plurisubharmonic functions here, which you can add to your original one, and then create a strictly plurisubharmonic function in this neighborhood of this boundary, and use that to prove holomorphic convexity. I mean, this requires some argument, but that's sort of the idea. So therefore, it's the for this one, continuous is fine. Because of the discreteness of the representation. So what happens is the original representation is not discrete, but because we are assuming it is rigid, we are taking. I'm not just taking GLN, but I'm taking its product with all the. Yeah, okay. That's what it is. So this is how we'll analyze here. So if this exhaustion function was generically strictly plurisubharmonic, then it's automatically holomorphically convex. So we just have to deal with when it's degenerate, which just means that the Levy form wedge itself is 0. Where in this case, yeah. No, sorry. No. All of these cases, the degeneracy locus is going to be sort of analytic because they come from holomorphic foliations. There, what happens is it's strictly plurisubharmonic away from a subvariety. And so then I'm claiming that it's holomorphically convex. So we have two possibilities, right? Look at DD bar phi. So either it's generically positive, or you have its wedge with itself is 0, right? If it's generically positive, I claim that it's holomorphically convex by that argument. So this means when its wedge is 0 with itself, you're saying that you have a codimension 1 foliation, right? Complex codimension 1 foliation. Except that in general, it need not be holomorphic, but in our case, it comes from a proper pluriharmonic map. So in particular, the leaves of the foliation lie in the fibers of the pluriharmonic map in some sense. So your foliation will be a holomorphic foliation.
So holomorphic means it's locally by holomorphic.
Morphic, yeah. In fact, yes. I've used it. I'll show you in a moment where I'll be using it. It's exactly in this situation I'll be using it. See, the main feature about the Cousin examples is, notice there is a proper pluriharmonic map to the line on those Cousin examples. Because if you have a Z covering, it's represented by a 1 form. So you can take the harmonic representative. So it will give you an equivariant proper map to the line. So you can look at the level sets. The level sets in those Cousin examples would be a 3 torus with a foliation with dense leaves. So the level sets are what they call Levy flat. So this is where this is going to come now. So we have phi to R here. So what do I want to say? Yes. So I'm going to assume so you have a codimension 1 foliation. So sorry. Any questions? Yeah. I mean, it's away from a codimension to complex codimension 2. Because holomorphic foliations, you can always ensure that the indeterminacy is complex codimension 2. So that means you get a bunch of points. Okay. No, in this case, it's going to be analytic. Yeah, sorry.
So how do you?
That's actually you have to use the more about the harmonic maps there. That's was done by Philippe, for example. Yes.
I'm sorry,
Yeah.
just something I don't understand. Here you have a Mohan foliation, basically, and
No, this foliation.
you treat it as it was holomorphic foliation. Then you have to say that it is a holomorphic.
Exactly. And so the point is, it is a holomorphic foliation because you're dealing with pluriharmonic maps to buildings and symmetric spaces. Otherwise, it's not a holomorphic foliation at all. Yeah. So yeah, no, this is, I didn't want to, see what really happens is you'll get that dd bar phi is greater than or equal to a semi-Keller 1-1 form, which comes from pulling back the inner product, complexified inner product on the symmetric space. And then in case of a building, you just take it on an apartment, you just take the form wedge its conjugate, and then it's invariant under the finite, the Weil group action, so therefore it gives you a 1-1 form. So you add all of them up. So these things are built out of holomorphic gadgets. So it is a holomorphic form foliation. Because I didn't want to deal with some of the technical issues that come up. So the idea here is you work in the following fashion. So either a level set of phi is real analytic Levy flat and compact. So you have one situation like this. So you start looking for the level sets. If this map was real analytic, then you get these Levy flat hypersurfaces. So this is where I use the fact that we don't have two ends, because two ends work. So what I want to do is the following. So here is a covering. So I'm looking at these Levy flat hypersurfaces, and because I have a big group acting, I can always translate it. So what I want to do is, if I remove these hypersurfaces, I want to get a manifold with at least 3 ends. And that's where I use the fact that it doesn't have 2 ends, because you could have this picture, and you remove these, all you're doing is you're just disconnecting it. So in such a case, from earlier work of Napier and myself, we showed that such things map properly onto a Riemann surface. Because these coverings have bounded geometry, it's enough to show some open piece maps properly onto a Riemann surface. Then just an analytic continuation argument will show that the whole thing maps properly onto a Riemann surface. So we have that situation. Or what could happen? This is where I'm going to use the fact that it's semi-analytic. After all, locally, what is it going to look like? You have this codimension 1 foliation, so you have a map to a disk, and then your plurisubharmonic function descends to this disk. So even if it's subanalytic, we know on a disk it's semi-analytic. So let's look at a level set. If it has a singular point, then the corresponding boundary of the level set upstairs is going to have 2n minus 2 dimensional singularities. But that set is closed. But the leaves also lie inside this set of the same dimension. So that tells you that the level sets do have some closed leaves. And if this is true for all such level sets, you're filling up your space by at least total of 3-dimensional versions of curves together. So again, a cycle space argument tells you that it fills up the whole space. So then you get a map to a Riemann surface. So that is sort of the key. So you play against either this Levy flat. If it doesn't, then the singularities do help you out. So that's the key here. So then, of course, you can ask what happens when the situation is non-rigid. So if rho is non-rigid, so we look at the corresponding component of the Betti moduli space, which contains rho. And what I do is, these varieties are defined over q bar. So therefore, I get the q bar points are dense. So I can just look at reductive representations of gamma into gln of q bar, a whole bunch of them, countably many of them. I'll call them rho sub I. So let's list. So these are all. Yeah, but that won't. What will happen is this: there is a large kernel between the original representation and the rho i's, right? So I have countably many, and I can find countably many so that the intersection of their kernels is the same as the original one. So here I need an argument because I end up dealing with the infinite tower of coverings, and then it's not clear anymore that the one up at the top has the right feature. So in fact, that's the goal now. So what we know is, so for each rho I, so m tilde mod kernel of rho I to m, this is holomorphically convex by the same argument as before. So now what we do is the following. So that means, so you get a proper map to a certain Stein space. So I call it yi. And then this group acts on yi, and then you get a quotient here. Okay. So which I'll call yi. Maybe I'll call it yi twiddle, and then the quotient of yi. So that means you have a map now from M to an infinite product of the yi's, right? So by the Noetherian property, this projection down to you can find finitely many factors such as the projection is an isomorphism. So that means it's enough to work with finitely many representations. Now what we do is look at the fibers of this map. That's Stein factored, so I'll pretend that the fibers are connected. So what do we know? We know that when you take any of these representations and look at the image of the fundamental group of this fiber, it's going to have finite image. So that means when we look at for each of the this will then imply that the original representation had to have finite image. Phi 1 of this fiber had to have finite image in the original representation. So therefore, what we have is we have a map from some product of these yi twiddles. And then we have our original covering, which is m twiddle. And what I know is the connected components of fibers when I lift up here of this map are compact. And therefore, I can Stein factor this map. So you can prove a slightly stronger version of Stein of this theorem that coverings of Stein manifolds are Stein. So this gives you a locally finite to one map from whatever, y twiddle, whatever, to this. The Stein factorization will be a locally finite one map to a Stein space. So therefore, it's also Stein. So that's how we argue that it's holomorphically convex. I think I'm done. Sorry. Thank you.